Hi, I am Suresh. Welcome to Rock Leaders. Today I am going to discuss about real numbers. So what do you mean by real numbers? Real numbers, a set of rational and irrational numbers. We'll see definition once again. Numbers are a set of numbers that includes all rational and irrational numbers, forming a complete and continuous number line. Here you can see that in the definition it's given that irrational numbers and rational numbers. See here, rational and irrational numbers. We'll go one by one. We'll see the definition of the rational numbers and the irrational numbers. Okay. So what do you mean by rational numbers? First we'll see the rational numbers. So rational numbers, those numbers, the numbers if I can write in the form of a by b, and b is not equal to 0. Here, so a and b are integers and b is not equal to 0. Here denominator not equal to 0. Then that number is called a rational number. We'll see once again the definition of the rational number. Rational numbers are numbers that can be expressed as a quotient or fraction of two integers where the denominator is not equal to 0. In other words, a number is rational if it can be written in the form of a by b, where a and b are integers. Here we are talking about integers. A and b are integers. And b is not equal to 0. This is the condition. b is not equal to 0. Rational numbers can be positive, negative or 0. And they may be expressed as their proper fractions. You know proper fraction means, so the fraction, the numerator is less than the denominator. So where the absolute value a is less than the absolute value of b, or improper fraction where the absolute value of a is greater than or equal to the absolute value of b. Rational numbers can be written as terminating decimals or repeating decimals. Okay, we'll see one by one what is mean by terminating decimals, what is mean by repeating decimals, and before that we'll see the definition of the integers. What is mean by integers? Here it is mentioned that integers. What is mean by integers? Go to by definition. So here this is very important. So when we are going to express about the rational numbers, so we have to know that what is meant by integers. Okay. So now integers means what? See here. Integers are a set of whole numbers that includes positive numbers, negative numbers and 0. They are here. See the definition. Integers are the set of whole numbers that includes positive numbers and negative numbers, and included 0. This is 0. Okay. Without any fractional or a decimal part. So in this, so one more point is that we have to see here, without any fractional or a decimal part. In this one, in these integers, there is no fractions and there is no decimals. So all are whole numbers only. Maybe 1, 2, 3, 4, 5, or maybe negative. So minus 1, minus 2, minus 3. So like that. So here there is no. So this is the very important point. So that's integers without any fractional or a decimal parts. They don't have any decimals and they don't have any fractions. This is called a integers. In essence, Integers are numbers that do not have any fractional or decimal components and can be either positive or negative. Yeah. So this is the part, this is very, very important for the integers. Integers are the set of numbers that includes positive whole numbers, negative whole numbers, and 0. In a mathematical notation, integers are represented as a, so like this here. So you know that number line, the number line we can represent 0, 1, 2, 3, they are the positive numbers, and minus 1, minus 2, minus 3 are a negative numbers. So positive integers. So positive integers are those 1, 2, 3 and so on. Represent values greater than 0. So yeah, so positive means greater than 0. Any number is greater than 0 is called a positive integer. So negative integers means, you know that minus 1, minus 2, minus 3 and so on. So it means represents values less than 0. We know that, it's in a number line. In a number line, it's a number line. So here this is the 0, and here 1 and 2 and 3 and so on. So if you come in this side, so towards the left side of the 0, so I'll get minus 1, minus 2 and minus 3. So these numbers are less than 0. So these numbers are, so here 1, 2, 3, these numbers are greater than 0. So greater than 0 numbers are called a positive numbers, positive integers, and which are the less than 0 are called a negative integers. Now what about 0? Yeah, so what about 0? Include as a non-positive integer. This is the definition of about the integers. So very, very important. So one thing is that integers means what? Maybe there's a positive numbers or negative numbers, and 0 included 0. And one more important point is that, say, they don't have any fractions or there is no any decimals. So this is the important point. So now here only that's a, so natural, this is the positive whole numbers and negative whole numbers. There is no decimals and there is no fractions. Okay, so now we are going to discuss about that important point, is that what is meant by rational numbers. Yeah. So rational numbers, so just now we discussed about the rational numbers. What is meant by rational numbers? So rational numbers, we discussed about the numbers which can be right in the form of a by b, and b is not equal to 0. And a here, so once again I'll go to the rational numbers. Yes. Here we discussed about, for this point I came to there, that what do you mean by integers? Integers we discussed. Now I am coming to the back to the rational numbers. What is mean by rational numbers? How can? So many students have a doubt in this matter. So this topic is that rational numbers. So now rational numbers, it's very easy if you understand the integers. So now here, any number, if I can write in the form of a by b, is saying that. Okay. So now I want to ask one question regarding, can you tell me that 4 is a rational number? Can you say the 4 is a rational number? Yeah, we can say that 4 is a rational number. Why? I can write 4 is in the form of a by b, in the form of a by b, and b is not equal to 0. I can write. How I can write? So here 4 is equal to, I can write 4 equal to 4 by 1. So we know that 4 by 1 means 4 only. So here, see that, according to our condition, so a by b, and b is not equal to 0. Here, a means, the definition, a and b are integers. So here see that, here 4 is integer, 1 also integer. That's why the condition is satisfied here, 4 by 1. So a by b, and b is not equal to 0. So you can say that 4 is a rational number. Now, see here. Okay. So can you tell me that minus 5 is a rational number? Yes, sir. You can say that minus 5 is a rational number. Why? Because minus 5 I can write in the form of a by b like this. Minus 5 is equal to minus 5 by 1. So minus 5 also rational number. So it means that all natural numbers, so natural numbers, you know that natural number starts from 1, 2, 3, 4, this is counting numbers. So these numbers are called natural numbers. All natural numbers are rational numbers. And we can say that, yeah, and whole numbers. Take a whole numbers. So, yeah, 0, 1, 2, 3, 4. So, whole numbers also rational numbers. Just now we saw that, so minus 5 is a rational number. That means minus 5 means, so minus, negative number. So, negative numbers are negative integer. So, negative numbers is called also integers. So, now here, so integers, so whole numbers we represent with the letter W. And integers. So, integers also rational numbers. Z. Integers represent with the letter G. So, integers also rational numbers. Now, so these are the come under all are come. So all are rational numbers. So natural numbers, whole numbers, and integers all are rational numbers. Now, here the point is that we discussed about what about irrational numbers. Okay, so rational numbers. Now you got an idea about that. So all are natural numbers and whole numbers and integers. All are we can say there are all are come under rational numbers. Okay, what do you mean by irrational numbers? So irrational numbers means that the numbers which we are not able to write in the form of a by b. Irrational numbers means what? So which we cannot write in the form of a by b, and b is not equal to 0. So these are which are not able to write in the form of a by b and b is not equal to 0. Then these numbers are called irrational numbers. You see, what are the irrational numbers? And we'll see the one by one with examples by definition. So here, irrational numbers are a class of real numbers. Yeah, these are the part of the real numbers that cannot be expressed as a simple fractions ratio of two integers, and they have a non-repeating, non-terminating decimal expansion. In other words, they are numbers that cannot be written as a quotient of two integers a by b, where a and b have no common factors other than 1, and b is not equal to 0. So this is the definition. So irrational numbers we cannot write in the form of a by b. Okay, so example. So common examples of irrational numbers include pi, root 2, root 3, and so on, and so many numbers are there. So we can see that one by one. So yeah, so we have a doubt. So we can write in that's root 2. Suppose root 2 is there. Yeah, root 2. Given an example, root 2. Root 2, this number, root 2, I can write in the form of root 2 by 1 also, no? Yeah. So you can say that, sir, the root 2 by 1 is in the form of a by b. And according to our definition, b is not equal to 0. Yeah. Then why not, sir? This is not a rational number. Why it's called a irrational number? That's why I told you in the beginning, so we have to know the definition of the rational numbers. The rational number says that, rational number said that A and B are integers. So we have come to back to this point. A and B are integers. It means here, okay, B is integer. B is equal to 1. Yeah, B is integer. What about root 2? Root 2 is an integer. Tell me, root 2 is an integer? No. We know that integer definition. So what is the integer definition? So see, once again I am going back to the integer definition. What the integer says that, so integers are the positive numbers, negative numbers and 0 without any fractional or a decimal part. Fractional or a decimal part. Called a is the integer definition. Okay, now here, so root 2, what is said that positive, what is the integer means? Positive or negative and 0. So this is the combination only. Integer means positive integers, negative integers and 0. This is the integers are. So here in that integers, you know that the number line, okay? So in the integers, if I take that integers 0, 1, 2, 3 and -1, -2 and -3. So in this you can see that there is no root. There is no root values. So that's why. So now here root 2 is not come under integer. That's why, so when it's not integer means there is no chance to discuss about this number is a rational number. Okay, so that's why root 2 is a irrational number. Got it? So here these numbers, example, so pi also irrational number. So these are the main important points about the rational numbers and irrational numbers. The one more important topic in our chapter is that the fundamental theorem of arithmetic. Let's see what is meant by fundamental theorem of arithmetic. Now here, yeah, the theorem one, fundamental theorem of arithmetic says that every composite number can be expressed, factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Once you can see here, every composite number can be expressed as a product of primes. Yeah, this is the main point. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Okay, now what is meant by composite number? Yeah, here is given that every composite number is said that. What is the composite number? First of all, you know composite number, then we'll go that fundamental theorem of arithmetic. One second. What is meant by composite number? Composite numbers, we have two types of numbers, so prime numbers and composite numbers. You know the prime numbers means what? The prime numbers are those numbers are called prime numbers which have those have only two factors, one and the number itself are called a prime numbers, and the numbers which has more than two factors is called a composite numbers. For example, I'm taking as a, suppose I'm taking 3. Here I can write 3 is equal to 1 into 3. 3 has only two factors, 1 and 3. The 1 and the number itself. If I take a 4, yeah, maybe a 6, I'm taking 6 example, 6, I can write in the form of 2 into 3 and 1 into 6 also, 1 into 6 also, yeah, right. What are the factors of 6? 1, 2, 3, 6. So here the factors are more than 2. So this number is called a composite number. 6 is called a composite number. Why? Because 6 has a more than 2 factors other than 1 and the number itself. Other than, it's a simple condition here, other than 1 and 6, if the number has any other extra factor, then that number is come under composite numbers. Yeah. But he said that once again, a product of primes, and this factorization is unique apart from order in which the prime factors occur. Means this factorization is unique. For us, unique means only single only. This unique means this is not we cannot will not repeat any other numbers. Suppose I am taking 8. What are the 8 factors I can write in the form of prime factorization? 2 into 2 into 2. For 6, 6 is equal to 2 into 3. So here this is called a uniqueness. 8 means 2 into 2 into 2 only. 6 means 2 into 3 only. I can write maybe the order, maybe we can change the order. So 3 into 2. But the same numbers from 3 and 2 only here and 2 and 3 only. So this is a unique. That's why saying that here what is saying that factorization is unique apart from order. So maybe that's order, maybe you can change. So 2 into 3, 3 into 2. But he is saying that this is the only, for 6 the factors I can write in the form of 2 into 3 only. There is no other way. There is no other factors. So this is the uniqueness of that. So now once again, what about the composite numbers? So here the definition of composite numbers. The composite numbers are positive integers greater than 1. Yeah, we know that. So this is a composite. What is that? Greater than 1 means are the positive integers. So composite numbers are positive integers greater than 1 that are not prime. Yeah, that are not prime. In other words, a composite number is whole number that has more than 2 distinct positive divisors. Example of composite numbers you can take. So 4, 6, 8, 9, 10, 12, 14 and so on. Okay, I can ask one question that what is the smallest composite number? What is the smallest composite number? Yeah, you can say that. So smallest composite number is how much? It's 4. 4 is the smallest composite number. This is about the fundamental theorem of arithmetic. Okay. So now we are going to, once again, so we will see that what is that. So here this is the important point. That's this theorem is very important. See once again. So theorem 1.1, fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So any number, this means say that any composite number I can write in the form of prime factors. Otherwise, I can write in the form of product of two numbers. Product of two numbers. Please remember this one, because when we are doing the sums, that time we will use this theorem. So first, so you know that. So any composite number you can write in the form of product of primes, or you can say that if any number I can write in the form of product of two numbers. Suppose here 8 is equal to 4 into 2. So because this is 8 is a composite number, I can write in the form of product of two numbers, maybe primes or maybe not. Other than primes also you can write. So this is so if I write any number in the form of product two numbers, that number is called a composite number. Now we'll see that exercise and examples. First example. So then we'll go to exercise one by one. So here example 1. What the example 1 says. Yeah. Example 1. Consider the number 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. Once again, consider the number 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. Means what? Suppose if multipliers, you know that 4 power n means what? 4 power n means, suppose 4 square means 4 into 4. 4 4 you know that 16. So 4 cube. 4 into 4 into 4 is equal to 64. Like this, we can continuously go on. He's saying that for n, any value, if that n, so the digit ends with the digit. So here this is the digit, how much? Here digit is 6. Here how much? Here is 4. Any number, if take a n 4 power, maybe 5 or 6, any number take power. So it ends with 0. That's the question. Is it ends with 0? Ends with 0 or not? Then how can I say? Yeah. So now for this, we'll see before, suppose any number ends with 0. That means if that any number ends with 0, that number, so we know that divisibility rule says that any number, suppose is a 20, for example 20 is there, 20 ends with 0. So we know that divisibility rule of 215. So a number ends with 0, it is divisible by 2 and as well as 5 also. That means if ends with 0 means, so these factors, suppose I am taking as a 20, write a 20 as a prime factors, 2 into 5. So it has a prime factors 2, 1, 5 only. Suppose I take as one more number, 30. So what is that prime factorization of 30? So 2 into 3 into 5. So now here in 30, you can see that 215 is there. Then 215, 3 is there. But so what is the common repeated ones is the 215. But take any number ends with 0 means, so that number has a 215 as a prime factors. Okay. So now coming back to the point where he's saying that, what is the question? So 4 power n can ends with the digit 0. So we know that, we'll see now. Yeah. So we now got an idea about that. If any number ends with 0 means that number must have the factors are the prime factors are 215. So I am writing is a 4 power n. 4 power n is equal to, I can write is a 2 into 2 whole power n. So now here 2 into 2 means here there is so it is in this one 4 don't have 5 as a prime factor. So when there is no 5 means, so it will not divisible by 5, and it means that this 4 power n will not end with 0. So therefore we can say by, because so here 2 into 2 4 power n. So now 2 means 4 power n is equal to 2 into 2 4 power n. So now here there is no 5 in this one. So I can write as 4 is equal to 2 into 2 only. So there is no 5. So therefore we can say that 4 power n not and with 0. So this is the way we can say that. So one more point, one more example we'll see here. Example number 2. Find the LCM and HCF of 6 and 20 by the prime factorization method. Second example, find the LCM and HCF of 6 and 20 by the prime factorization method. We know that prime factorization method means what? I think we maybe in a 6th class onwards we are doing that prime factorization method. We'll see now. If you don't know, so once again I am going to explain. Please concentrate and see. Find the LCM and HCF of 6 and 20 by the prime factorization method. I am taking as a 6. How to find the LCM and HCF? First I will write for this. First I write that prime factors of 6 and 20. Prime factors of 6. We know that. So 2 into 3. What is the prime factors of 20? How to write prime factors of 20? Okay. Now see here. 20. This is the method. This process is called a prime factorization method, and 2 table, 2 tangent. And 2 table once again, 2 5. Now here, so 2 and 5 are prime numbers. So I can write like 20 is, I can write like this, 2 into 5. So I wrote all the prime factorization of the 6 and 20. Now we are going to find the LCM and HCF of them. Okay, so I can write like this. This one I can write 20. I can write here a 2 into 2, 2 square into 5. Okay. Now see here. So what is the LCM? Now LCM. LCM is equal to. So I have a. So we know that LCM means. So generally, so LCM means so we'll take that. We'll see first common. So here 2 and 2 are common. So when they are common, we will not write twice. Why? Because repeated ones we will not write. We will take as a single. Then for this, so here common 2 is coming. That's why 2 into remaining numbers. We will multiply the remaining prime numbers also. So 2 into 3 into 5. Yeah. 5. So what is the LCM? 2 to 4, 4 to 12, 12 5 to 60. 60 is the LCM. What is the HCF? What do you mean by HCF? HCF means highest common factor. Highest common factor. Now see here, it must be common factor. Okay, so now here 2 and 2 only common. So in this one 6, if I take a 6 and in 6 and 20, there is only 2 is common. So we can say that. So 2 and 2, these two only common. Is equal to 2. LCM is 60, HCF is 2. Now, if you what you observe here, see that what we observe in this one. Here I wrote in the LCM, see here the numbers, I wrote in the powers, so here, this I can write as a, see here, once again I am writing this one, 2 power 1 into 3 power 1. Here I can this can write as a 2 square into 5 power 1. So now when, observe here, 2 power 1 and 2 square. So here powers are, which is power is here, 2 is the power, is the, so more power, that's the greatest power. Which is the greatest power? So product of the greatest powers, the numbers which has a more powers, greatest power, the two common numbers, there are two common numbers, 2 and 2 is common. So which has the greatest power? So that will take as a 2 square and product of the remaining numbers. So here when we are talking about that what is the LCM. So LCM means what? How can we do this one? Simply, so when which has a more powers, which number has a more power, so that number will take. That factor will, that prime number will take. So here 2 times 2 square and remaining. So which is the, which has a more, the product of the, which number has a more powers and the remaining, so numbers will multiply, will get the LCM. This is the LCM. Now here for the HCF, for HCF, it is given that, so we observe that, so only, now here 2 power 1 and 2 power 2. Oh, see here, we observe. So here 2 power 1 and 2 power 2, which is less one, so only 1 is. So and that time, so here, what mean by HCF? HCF will take that to least power. If 2 powers are there, 2 common numbers are there, 2 common factors are there, then one which is the least power, and will take that to least power, product of the least powers. So here, this is the common factors, only 2 and 2 only here. So here 2 power 1 is the only 1 power, so we'll take as a HCF is a 2. Understood? This is the way we can find the HCF of the numbers. Now we are going to discuss about, we are going to solve that exercise 1.1 first question. What is the first question? Yes. Express each numbers as a product of its prime factors. Express each number as a product of its prime factors. You know that? He said that only. So express the numbers as a product of prime numbers. Yeah, prime factors. 140. First question I am doing. First Roman. 140. 140 is equal to. How can we write? So how we know that? How to do? We know how to do this 140. I am taking 140. 140. Two table, 2 7 ja, 14 and 0. Once again 2 table. 2 3 ja 6. So 1 will left. 1 0 10. So 2 5 ja 10. Once again. So now 5 is ends with 5 is 5 table. 5 7 ja. Now 140 is equal to, I can write as a 2 into 5 into 7. So this is the answer. Express each number as a product of its prime factors. This is the number. Next one, second question, second Roman, 156. You can say that. So I can write like this, 140 is equal to, I can write here 140 is equal to, I can write, this is the form of 2 square into 5 into 7 also. So tell me what are the prime factors of 140. So prime factors of 140 are 2, 5, 7. Now second question, 156. Yeah. 156. How can we do 156? 156. Similar way, we'll do with the 2 table. 2 7 ja 14, 1 6 16, and 2 8 ja 16. Once again 2 table. So the students are confused. Still they are confusing that how to do this method. So many students are still they are confused because their foundations are properly not proper. That's the reason. So once again, see, I am going to explain. I am explaining slowly one by one. So here 7 is there. That means 2 3 is 6. 2 3 is 6. And 7 minus 6 is 1. So I am writing here 1. So it becomes 18. So 2 9 is 18. Now this will be 39. So we don't know what is the 39 means, is the prime number or any other. So that time if we have a doubt, so we have a divisibility test, 2, 3, 4, 5 like that. So now here 2 table will not come. Why? Because 9 is there, 9 is not divisible by 2, that's why it is not divisible by 2. It's over. Next you will check for 3. So 3 plus 9. So divisibility test of 3 is the sum of the digits. If I add the sum of the digits and the sum of the digits divisible by 3, that number divisible by 3. So here 3 plus 9 is 12. So 12 comes in 3 table. 12 is a multiple of 3. So that's why I can take as a 3. The 3. So 3 1 is 3, 3 3 is 9. Yes. So 13 is a prime number. Now I can write 156. 2 into 3 into 13. So this is equal to 2 square into 3 into 13. So what are the prime factors of 156? You can say that 2, 3 and 13. Next question. 3,825. 3,825. Okay. How to do? The same method. The same method we use. We know that prime factorization method. The procedure. 3,825. Now tell me which table. So we'll go for 2 is not there. 2 table is not possible. For 3 table I'll check. So 3 plus 8, 11. 11 plus 2, 13. 13 plus 5, 18. That means it will be divisible by 3 table. Now 3 1 is 3. 3 2 is 6. 6 2 will be left and 22. 3 7 is 21 and 1 here. 3 5 is 15. Once again I'll check for 3 table is possible or not. So 3 7 10, 10 plus 5 15. Yes, 15 comes in the 3 table. So 3 4 is 12. 3 2 is 6 and 1 here. 3 5 is 15. Now check once again with 3 table. 4 plus 2 6, 6 plus 5 11. So it is not comes in the 3 table. So 5 is there. That will go by 5 table. 5 8 is 40. 2 will be left here. 25. 5 5 is 25. Once again here 5 is there. So 5 table. 5 1 is 5. 2 3 3 will be left. So 8 minus 5, 5, 8 minus 5, 3, 35. 5, 7, 35. Now 17 is a prime number. No need to do. So now here 3 into 3 into 5 into 5 into 17. 3 square into 5 square into 17. This is the final answer. We can express this given number in the form of product of primes. We'll go for second question. So remaining questions, please try it and practice, and we'll go for next question. Second question. Find the LCM and HCF of the following pairs of integers and verify that LCM and HCF is equal to product of the two numbers. What is that? He is saying that for the question, find the LCM and HCF of the following pairs of integers and verify that LCM and HCF is equal to product of two numbers. Yeah. We know that how to do. So we'll go, just now we discussed about first question. So first we write all the prime factors, then we'll find LCM and HCF. First question. (26) and 91. Yeah. First we will write, you know that procedure, so we know how to do. So first we write the prime factors of 26. We know how to write prime factors of 26. 26. This 26. 6 is there, 2 table. 2 1 ja, 2 3 ja. Oh. 13 is a prime number, 2 was prime number, and itself 2 into 13. Now 91. Yes, 91. I'll go by 7 table. 7 is 7. 2 left. 21. 7 3 is 21. Yeah, 13 also. Yeah. So 7 into 13. They are the prime factors of 26 and 91. Now, the question, find the LCM and HCF and also product of the numbers. Yeah. LCM of, yes, LCM of 26 and 91 is equal to. What are those? You know that LCM means, we will take that all the, so which one is repeating, so that we will write only once and remaining numbers we will write all the, we will write all the remaining prime numbers and multiply. Now here 2 is there, 2 is single, 2 and 7, and we can see that 13 is a common factor in this one, 13. So I'll take 13 as a only one time 13. Yeah. Now 37 ja, 91, 91 2 ja. So you know that, so 91 into 2, how much? So 2 18, 182. So this is 182. What the LCM of 26 and 90? is 182. Next question. Next part is that find the HCF. What is the HCF? Yeah. HCF. HCF is equal to HCF of 26 and 91 is equal to HCF will take only that highest common factor. Highest common factor means, so what is the highest common factor here? Here highest common, this is the common factor, 13 only. So what is the answer for this? HCF of this for 26 91 is 13. Okay, yeah, we got it both. Yes. LCM and HCF, we get the answers of HCF and LCM. What is the question? Yeah. What is the question? Verify following pairs of integers and verify that LCM into HCF is equal to product of the two numbers. Now we have verified. First we will find that LCM into HCF. LCM into HCF is equal to 182 into 13. 182 into 13. We multiply 182 into 13. 32 is 26. 13 8 is 104. 104 plus 2, 106. 106. Yeah, see here, putting here. Yeah. 13 1 is 13. 13 10, 23. 2366. 2366. Now we'll go for product of the numbers. Product of the numbers. Product of the numbers. What are the numbers? 26 into 91. So see here, multiply and we'll get rough work. 26 into 91. 6 2 54 4 5 18 523. 6 6 3 2. So we got 2366. See here, both are same. So we can say that LCM into HCF is equal to product of the numbers. So here result is verified. You can say that the conclusion. Result is verified. So this is the final answer. So what we concluded here, that so LCM and HCF is equal to product of two numbers. Only this will be valid for only for two numbers, not for if you are taking as a three numbers, and if I find LCM and HCF, if I do this this one, then we will not get. So this is only for valid for only two numbers only. So LCM of two numbers and HCF is equal to product of the two numbers. Okay, we'll see in that next questions also. Now question number 3. Find the LCM and HCF of the following integers by applying the prime factorization method. Find the LCM and HCF of the following integers by applying the prime factorization method. Yeah, you know that. So prime factorization method means, just now we did first question also, second question also, and the third question also same way. But here we have three integers are given. So we will do one question even. So we'll go by which number? 12, 15, 21, 17, 23, 29. So yes, second question, see here. The second question, 17 is a prime number, 23 also prime number, 29 also prime number. Then what the LCM? So when they are prime numbers, we have to multiply three numbers, then we get the answer. No, directly. There is no. So we know that. So if we write second number, second question, second question. So LCM of. Oh, sorry. Yes. LCM of 17, 23 and 29. So what we do? First we have to write prime factors of 17. 17 prime factors. So 1 into 17. So there is no, because this is a prime number. 23. 1 into 23. 29. 1 into 29. Here, if you see, 17, 23 and 29 are prime numbers. So what are the LCM? LCM is equal to LCM is equal to 17 into 23 into 29. There is no common, so this is the LCM of 17, 23 and 29. Multiply, so we will get the answer. So what is the answer for this? Let's see, 17 into 17 into 23. Sorry, first I'll do that. 17 to 23, 17 to 23. Values directly. 23 into 17. 73 is 51. 72 is 34, 39. Into 29. 9, 81, 9 9 is 27, 27, 35. Yes. Just a minute. Yeah. 2 table. 2, 18, 1, 6, 7. 9, 3, 13, 1, 10, 11. 11,000 339. This is the final answer. See here, this is the, if they are all prime numbers means there is no there is no common factors. That's why we multiply all we multiply all the numbers, all the integers, we get the LCM. What is the HCF? Yeah, HCF. HCF, highest common factor. Yeah, in this case, what is HCF? Now see here, HCF is 1, 1, 1. Here, 1 only is the common. Which one is the common? So here only 1 is the common. So HCF is, we can write, HCF is 1. HCF of 17, 23 and 29 is HCF of HCF of 17, 23 and 29 is how much? 1. This is the HCF of this number. Remaining questions, I think you know that remaining are, so yeah, I'll do one more question for you. Go for third Roman, 8, 9, 25. 8, 9, 25. Third Roman, 8, 9, 25. Third Roman. Eight, 9, 25. You know that how to do? First of all, same method we apply. We'll write all the prime factors of 8. Yes. 8 prime factors. 8 is equal to 2 into 2 into 2. 3 prime factors. Sorry, 9 prime factors. 9 is prime factorization. 3 into 3. For 25, I can write 5 into 5. Yeah. Then what is the LCM? Here, there is no common factors. All are different. See here, there is no common factor. Now 3. So when there is no common factor means we have to multiply all the numbers. So LCM of 8, 9, 25 is equal to how much? 2 into 2 into 2 into 3 into 3 into 5 into 5. It means you are multiplying all the 3 numbers. Once again, it seems there is no difference between the prime numbers and these also this composite numbers combination. No. You know that here this is the 8, 8 9 ja 72, 72 25 ja 72 into 25, 10, 1, 35, 36, 4, 14, 0, 0, 8, 1 is equal to 1800. This is the LCM. What about HCF? HCF, you can see here, in this one, there is no common. There is no common factor. So HCF means highest common factor. So now here there is no highest common factor. This it means that is a 1 only. So there is no common factor means that answer will be 1. So HCF of 8, 9, 25 is how much? 1. This is the answer. Question number 4. You directly go. Question number 4. Given that HCF of 306 and 657 is 9, find LCM. Find LCM. Yes. We know that just now we discussed in the previous question, product of two numbers is equal to product of HCF and LCM. Here HCF is given, find the LCM, and we give two numbers in the question, the fourth question. Okay. Yeah. Given that HCF. Now, what the formula? Just what is that formula discussed? Product of HCF into LCM is equal to product of two numbers. Product of two numbers. Yeah. Now product of HCF and LCM. HCF and LCM. This is the formula. Okay. So we know that what are the numbers? The numbers what are the numbers is equal to 306, 657, the numbers, and HCF is given. HCF is equal to 9, and we had to find the LCM. LCM is how much? Okay. So according to our this one, HCF into LCM. HCF 9 into LCM is equal to product of the numbers 306 into 657. Yeah. LCM is equal to, see here, LCM. You know that LCM is equal to 306 into 657 by 9. Yes. Now 9, 3 table. So here 306, 3 table. 3 3 ja 9. 3 1 ja 0, 2 ja. Once again 3 table. 3 1 ja 3 3 ja 9. 1 3 4 ja. So is equal to. Now I can write this one is equal to 34 into 657. What the answer? Multiply these two, will get the answer. 34 657 multiply by 34. Yeah. 4 7 are 28. 4 5 are 20. 22. 4 6 are 24. 26. 3 7 are 21. 15 to 17, 1, 3 6 18, 119. Oh, sorry. Can write this one. Eight, 3, 13, 1, 12, 2. So 34 into 657 is equal to 22,338. This is the LCM. Got it? Next one. Next question. Fifth question. Check whether 6n, not 6n, this is 6 power n. 6 power, check whether 6 power n can be ended with the digit 0 for any natural number n. We'll discuss. We discussed the first question itself, first example. It says that 4 power n can end with the digit 0 or not. So that I explained that. So any number ends with 0 means that number must have a 2 and 5 as a factors. So now if the number divided by 5 means it definitely ends with the 0. Now here 6 power n, I can write 6 power n is equal to 2 into 3 whole power n. Now here in this one 6 power n, in the 6 there is no 5. So only 2 into the 6 does not have 5 as a factor. That's why, so we can say that 6 will not end with 6 power n for any number, for n, any number, any natural number will not end with 0. So this is the why, because 6 is not a, 6 is not have a 5 as a prime factor. That's the reason. Okay. So next one, go for sixth question. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Explain why. Yeah, first of all, we know that we need to understand that what is meant by composite numbers. Composite numbers are those numbers. Composite numbers means, so which number I can write in the form of product of two numbers. That's it. Of course, composite number means you can write in the all composite numbers. Any composite numbers you can write in the form of product of prime numbers. That's another definition, and we can say that. So composite number you can write in the form of product of two numbers. If any number if I write in the form of product of two numbers, then there's a composite number. Now see here, we'll check that whether we can write this number in the form of product of two numbers or not. We'll see here. 7 into 11 into 13 plus 13. See. I can write. So what is this? 13 is the common is there in this one. So here 13, here also 13 is there and 13. I can write this is like this 7, 13 I am taking common. 7 into 11 plus 1. Okay, so now you can write this there 7 13 into 7 11 ja 78 77 plus 1. 13 into 78. Yeah. Now see here, we can see, so this given number I write in the form of 13 into 17 as a product of two numbers. Then you can say that 7 into 11 into 13 plus 13. 7 into, therefore we can say 7 into 11 into 13 plus 13 is a composite number. Is a composite number. Composite number. Next question, next part. 6 into 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Yeah, you can also, this also you can write. We'll see how to write, whether we can write or not. What's the question? 6 into 5, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Okay. Second part. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. This is the question. Is this question can be this one is a composite number or not? Okay, now see here. If I write this number in the form of product of two numbers, a product of the numbers, then it is a composite number. Now in this one, 5 is common. I take 5 is common. 7 into 6 into 4 into 3 into 2 into 1 plus 1. Yeah. Now see here, this also you can see that this is a one number and this is a whole as a one number. So two numbers are there. This is one number, this is one number. So you can write this number as a product of two numbers. That's why you can say that. So 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Yes. Seventh question. I think so. We have to multiply and we can write this. If you want to answer, I can write the answer 5 into. So I'll take a black color. Yeah. 5 into. Multiply this all things. So 7 6 ja 42, 42 4 ja. 8, 16, 3 ja into 3, 24, 18, 20, 30, 35 into 2, 80 plus 1, 100, 1009, 1009. So what is the conclusion? So 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Why? Because I can write the number in the form of product of two numbers. So therefore, you can say that 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Yes. Last question for this exercise. Yeah. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the the question is not complete information. Both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? This is the question. Sonia and Ravi. So in this question, Sonia, this is the field, sports field like this. This is a running track. In this running track, they started here. They both started. This is the starting point. Suppose Sonia and Ravi. They started here. For Sonia to complete one round, she takes how much? She took 18 minutes to complete one round like this from started here and reach here. She took 18 minutes. For Ravi to complete one round, for him time is a 12 minutes. Then if there goes on continuously, then to meet at this point, what's the question? After how many minutes will they meet again the same again the starting point? Okay, they are going, so they are circling on the ground, they are running. So when they will meet, when they will come and then they will meet at the same point. So what to do? So here such question we have to find. So LCM. How we can solve this question? By finding the LCM. Because you know that, so when both are running on the track and after some time they will come and meet the same point, when how can solve this one? By taking the LCM of these two numbers. LCM of these two timings. Now, so for to find the LCM, what to do we? So we have to, so LCM of 12 and 18. I take LCM of 12 and 18. So for that, we have to know that the procedure. So first we write all the prime factors of 12. So what are the prime factors of 12? So 12 2 6 ja, 2 3 ja. That means 2 into 3. 18. 2 9 ja, 3 3 ja. 2 into 3 into 3. So LCM of 12 and 18 is how much? So I will write here a little bit. 18 is equal to, here see that LCM means here 2 is common here and here 3 also common. Yes. So remaining. So 2 into 2 is 2 into 3, here 1 3 we will write. 4 4 is 12, 12 is 36. After 36 minutes they will meet at a starting point. Thank you for watching. Don't forget, like, share and subscribe. Once again,